Yeah, let's recap quickly from what we discussed yesterday. So yesterday I in detail introduced this parametric representation of the Feynman integrals. So Feynman integrals roughly are these integrals. And we learned that we can write them as modulo some prefactors as these integrals over projective space. Where we integrate over a couple of objects, a couple of rational functions. And the volume forms this canonical form on positive projective space. This V here is the point where the kinematics enter, and the kinematics are relatively tame if we are in the Euclidean regime, meaning that we are choosing, say, for instance, an all-negative signature spacetime metric, and then this V is always positive. And so this term here is always negative, but we can just pull out the overall minus sign. And we only need this I epsilon in case the V can change sign to sort of avoid these poles that can show up in the integration domain in the right direction. But today I will only talk about this Euclidean case because there the theory is kind of complete, and lots of parts of the theory still work if we are outside of this Euclidean regime, and there are ways to repair it, but there are a couple of problems. And this is also what this makes this still a very interesting subject. So this V, it turns out to be a rational function that can be written as a quotient of two polynomials called f u. So u is the same u is here, and f is a different polynomial. So it's easy to check from this determinant formula that this is a polynomial. And this f as well, just by expanding this inverse of the Laplacian in terms of the adjoint of this graph Laplacian. And they are homogeneous. As they should be, because we are integrating over projective space. So these integrals, they should be invariant under rescalings. And actually, I forgot something here. So this is, we also need the sum of all the Schwinger parameters down here in front of the epsilon to be completely correct. And what I also want to mention is that for these polynomials, the u and the f, that they are combinatorial expressions for them. So one can write down formulas in terms of the structure of the graphs for them, at least in the scalar case. For the cases where we have numerators or where we have linear propagators and so on, there are no nice combinatorial, or I don't know any nice combinatorial formulas for these polynomials, but it would be great to have them for many applications. So the first thing today is maybe like another little exercise in projective diffeomorphisms. So we can still rewrite this representation one more time. And to do this, I now kind of pull out the overall signs and forget about the I epsilon, such that I only have like positive things in this representation here. So I want to forget about this minus sign, pull it out, forget about this I, And as we are in the Euclidean regime, we can also forget about the I epsilon for now. And in this case, we can use, again, a diffeomorphism from Rp E minus 1 cross Rp1. So this is also relatively standard to RPE. So we take the coordinates of this thing, and here we have homogeneous coordinates also in these edges, but we have the extra variable, which I call x star. And here we have, say, x1 prime, xa prime, and xb prime. And here we have the old edge variables, Schwinger variables. And we use this extra information here to just rescale like this x star parameter. So say, for instance, x star is xa, and these new edge variables are just xb times the primed x variables. And if we use this kind of diffeomorphisms, we can show further identity on the Feynman integral and change to the so-called Lie-Pomeranski representation. You can write I of g as some prefactor. So let me write out the prefactor. Pardon? Would you write a bit bigger, please? Yep. Is this big enough, or? Yeah, it's more from the coordinates of the practical spaces there, for example. I cannot read the topic in this of. Yeah. Which coordinates can you not reach? The one below RG1. Does it say XA? Yeah. Yeah, that's XA prime. So maybe a bit better. Thanks. So if you use such a diffeomorphism, one can prove that this is equal to an integral over Rp e, these Feynman integrals, Rpe plus. So I forgot the plus here. And also up there. And now we have only a single polynomial. This is the advantage in the denominator with this representation. And then U polynomial is now in the same denominator with the F polynomial. So this is like a more compact representation of these integrals, say in the Euclidean regime. And we sacrifice, the sacrifice we have to make is like introduce one new dimension to the integral. And if you look at it more closely, there's another sacrifice, namely that the convergence of this thing here is worse than the convergence of this thing. And if you prove this, so as an exercise, you can prove this. And what you have to know is just this beta function integral. So you need to know that that this quotient of gamma functions equals this integral over Rp1. So that's the fiber integral that I omitted here. So this is the example integral from yesterday. Yeah, so this is also a nice little exercise to work out the details of this diffeomorphism and integrate over the fibers. And over the fibers, you just need to know this integral. And this generates you this prefactor change here. And what we win with this is that here we are now in the realm of like a very simple integral representation of so-called generalized Euler integrals. And so everything also works transparently with these like slightly more complicated representations where we have more complicated rational functions and also something in the numerator here. But here one has to write a bit less, so I prefer this representation for now. So now we can get rid of the physics and we can go completely mathematical because we are in this realm now of these integrals. So we now can go to complex analysis and ask them about these integrals. So we are of so-called generalized Euler integrals. And this is a very beautiful theory of these integrals. So as an input, we take a general polynomial, which is homogeneous. And we can just write down an integral that depends on some parameters, like these nus. And we define it to be an integral over the positive n minus 1. So say this is a polynomial in x1 to xn. So we integrate over n minus 1 dimensional positive projective space. And here we raise these x's, the homogeneous coordinates, to these parameters, these new parameters. And then we divide by this polynomial raised to some power. And the canonical form is the volume form. And because we want this to be a real good projective integral, we need to require that this power s here, that s is compatible, so that this x up here have the same scaling behavior as this homogeneous polynomial down here. So we need to require that the sum of these new I indices is equal to s times the degree of p. So each homogeneous polynomial has a definite degree. And there's a different requirement still that can be loosened also quite much, but I'm not going to talk about this so much. The requirement is that the coefficients of these polynomials, of this p polynomial, are positive. So p of x should be some polynomial, and it has some indices, and I use multi-index notation. So this k is some tuple of indices, say in n too small in the positive or non-negative integers, and it's a long summation. And these coefficients of these AK coefficients, they depend on these multi-indices. And for each coefficient, we have one monomial, and then we take the sum and raise each monomial to the power of this respective index of this multi-index. And here the important thing is that these coefficients, they are supposed to be positive. In the Euclidean regime, this is fulfilled, so we can make sure that they are always positive. Like I explained in the Minkowski regime, we actually also have negative coefficients, and there are generalizations of this theory where it's not necessary that the coefficients are strictly positive. We can also have complex coefficients and all this, but for sake of simplicity now, we are requiring that they are positive. And there's one way to think about these integrals. We can think about these integrals as functions of these new parameters and of the coefficients of this polynomial. So in a way, we define a function in these news and in these AK coefficients. And this is also the idea we take over from the Feynman integrals, because here these Feynman integrals, they're also functions of the dimension of the nu, and inside of this, the interesting part is also the dependence on the masses and the momenta. No, I need. So there's a nice reference on these integrals, which is a paper, very readable paper, that I want to mention. So, good reference by Nielsen and Passare. It was also mentioned at the conference last week in the talk by David Kosover. Can find it on arXiv. It's from 2010. And they discuss like the parts of the theory that is relevant for the Feynman integrals, at least, of these generalized Euler integrals. And the key tool one needs to know is some convex geometry. So we need to know a bit about polytopes to deal with these integrals. So this is essential. And I mean, who of you knows what a polytope is? Who knows what a Newton polytope is? Who knows the V and the H representation of polytopes? Okay, not so many. Okay, but yeah. So I'll be brief then here. So the Newton polytope is, so in general, like this polytope stuff, it appears a lot in the scattering amplitude business. So it's also good to have that in your toolbox. And if you already know about polytopes, maybe you will know something about facet representations and convex hulls that you can also add to your toolbox, which is very useful. So first of all, polytopes. Polytope is just a geometric object with flat sides, and the flat sides are called faces. And we can define a polytope as the convex hull of a couple of points in n-dimensional space. So the convex hull of a set of points so for instance, V1 to Vm in Rn, it's denoted as, say, so this is going to be a polytope, and this is, so we have the convex hull of these points. And this is just the set that is swept out by all linear combinations of these points in Rn, where the coefficients sum to 1. So we take linear combinations of these points, but we only sweep over all coefficients that form a simplex or just sum to 1. And this is going to give us a subset of Rn, and this is going to be a nice polytope. So as an example, say we are in R2 and we have 3 points given. Then the convex hull, it just sweeps through all the points that lie in between those 3 point coordinates. Yes, sorry, yes. Right. And this convex hull representation of these polytopes, of the polytope, is called the V representation for vertices. And there's also a different representation of a polytope, because each polytope can also be written as a set of inequalities that describe the polytope. So this is called the H representation by linear inequalities. So these are then inequalities or a couple of equations, say in Y. And we have many of these equations indexed by coefficients A and B. And so this is like a matrix equation here, of course, and the short form is of this is just to say that we are multiplying these y coordinates here. Y is some vector in Rn with some matrix A, and then coefficient-wise, and this inequality here is now then set up coefficient-wise. this is supposed to be smaller than some vector b. So we can also write little vector errors to do that. And now a polytope is just described by all y's that fulfill this condition. So also this sweeps out a polytope. And so these are the two important representations of polytopes. And what you need to know is that computationally, it's often a very hard problem to translate from one side to the other side. I mean, with computationally, I mean, it's not conceptually a hard problem. So you can just ask the computer to translate for you from this vertex representation to this inequality representation and vice versa. But it takes some time to do this, especially in higher dimensional cases. And it's kind of a non-trivial operation for computers. And people wrote like many complicated, dedicated computer algorithms that just perform this translation back and forth. Yeah, so, yes?
The superscript on the K and Y at the top should be 1.
K and Y M.
In the first.
Yes, sorry. Yep. Right. Squeaky now. Also doesn't work so good. Okay, so now Newton polytopes. So they are just polytopes associated to each polynomial. So let's say we have such a polynomial as we had above there, some coefficients ak, and these multiply the monomials. Then the Newton polytope of the polynomial is just defined to be the convex hull of all the vectors of the index set K. So here this n-dimensional index set for which the coefficient is non-zero. So yeah, this is a very simple definition. As an example, the easiest example is just a linear polynomial. And there we have two indices, say 2 vector 1 and 0. And here we have a 2, 0, 1. So the convex hull of K1, K2. Can just draw it in two-dimensional space. So this is the one axis and this is the two axis. And this K2 is now this vector and K1 is this vector. And the convex hull is all the points that lie between in these 2 points. So in this case, the Newton polytope is a one-dimensional object. It's just a line segment between these 2 points. Use this board. Maybe let's just do one more, slightly more complicated example. Suppose px1, x2. The polynomial looks like 1 plus x1 plus 4x2 minus pi I x2 squared. Then the coefficients again don't really count. It's just the powers and the variables that count for the definition of the Newton polytope. So this has all 0 powers. So this gives us a vector 0, 0. This gives us a vector 1, 0, because it has 1 power of x1. Here we have a vector 0, 1. And here we have a vector 0, 2, because it has 2 powers of x2. And the coefficients don't really matter. What matters is just that the coefficient is not 0. And if we draw this, then we have, you say, K2, K3, K4. We can again have K1 here, K2, actually this is K2. K1 is now at the origin, K3 is here, and K4 is here. And the Newton polytope is this triangle that is wedged out by these points. What's interesting here is that K3 is not a vertex of the convex hull anymore. It's just inside the polytope. And yeah, there are computer programs to do these kind of computations. For instance, so computer programs. For instance, there's Polymake, where you can ask the computer to do that. Okay. Now I'd like to state the first main theorem.
Sorry, hi. How do you decide which Ks to join up? So for example, you could join K2 and K3. Does it have to be a full like polygon or? Yeah.
What's the
So like in that one with K1, K2, K3, K4, like you
Yep.
join them up so it's triangle, but could you not in a different way join the points up by connecting K2 and K3 and then having a line up to K4, for example?
this is just about all the different points that lie inside this triangle. So you
Right.
can actually forget about the individual labeling that I put up here. The
Okay.
important thing is that you just sweep out all the space that lies in between all the points.
Okay.
So in a way, you can forget about K3, and you just remember that this is a triangle-shaped object in space, in 2 space.
Okay, cool. Thank you.
So this first main theorem tells you if such a generalized Euler integral is finite or not. And ultimately, this is also the way where you can always tell, or almost always tell, in case you're, so except in these cases where you run to these bad Landau singularities, you can tell if a Feynman integral is finite or not. And ultimately, the knowledge or the content of the theorem can be extended to evaluation algorithms. So saying if it's finite or not is already, or surprisingly, already half the way of the actual evaluation of this finite number. Let's say. So this is about finiteness. So such an integral up like the one up there, so this I nu one. So if we take this one with p as above, and p has positive coefficients. So we remember those conditions from above. Then this integral is convergent if and only if the vector that is formed by the nus, so this is nu1, nu(n), it lies inside the interior of the Newton polytope of P scaled by S. So we have to compute the Newton polytope of P, scale this Newton polytope out by this power S. So in a way, if it's an integer, then we can see that we are just rescaling everything by this value of S, and this is also compatible with just taking a power of this polynomial. And yeah, so this is the condition that we have to lie in this interior of this Newton polytope. I will explain later why this is true, so we'll give some idea of the proof. But for now, I will just give an example. Yep. The question is if there are any bounds on the scaling and if it can be an arbitrary real number. The S, you mean? Yeah. Yeah, so implicitly, such that this thing makes sense, you need the S to be positive, but you can actually also, it's enough to, yeah, so if you want to have complex coefficients there, you can also say you only want the real part to be positive. That's actually sufficient.
Okay.
So,
Thanks.
but the scaling it to be negative does not really work. No. So S, it has to be larger than 0.
So you can't flip it on anything. You can't flip it on anything.
No, I mean, if you flip it, no, you need some damping on the boundaries. That's not. So the issue is that this canonical form, it has poles on the faces of the integration domain. So you need something that dampens this these poles out.
I have a question as well.
Thanks.
Yep.
How does this work in the case of the original parametric representation where you had polynomials in the numerator and denominator?
Yeah, so I went to this Lie-Pomeranski representation because I wanted to only give you the simple case, But in this more complicated case with the numerators and the denominators, you have to have some containment of the Newton polytope of all the stuff that is in the numerator. So the Newton polytope of this stuff has to be contained in the Newton polytope of the denominator. So it's a bit, yeah, so you draw the polytope and it's fine if the other polytope just completely lies in the interior. But here we are in the simpler case where we just have draw the polytope and if the point, this new vector is inside this Newton polytope, then it's convergent.
Thanks.
More questions? All right. So maybe a small example. So here we already computed a Newton polytope. This is kind of a trivial example, but sometimes trivial examples are also kind of useful. So this is again this Euler integral, which corresponds to the bubble Feynman integral. So if we want to check if this is finite or not, we have to compute the Newton polytope of this denominator, which we have done here. And the only thing that we need to check is if this new vector lies in the interior of this Newton polytope. So it can sweep like through all the points that lie on this line between coordinates that are scaled here by nu1 plus nu2. And effectively what we find is that it's convergent if nu1 is larger than 0 and nu2 is larger than 0. And here I have to emphasize that this interior really means that we are not allowed to lie on the boundary. So if it lies on the boundary, we have a divergence. We have barely a divergence, but there's a divergence. So interior means that we really have to be inside. So cannot go to the boundary. Have to avoid the boundary. So this is a simple example, maybe a slightly more complicated one on a different blackboard. Let's say we have a more complicated integral. This is also a Feynman integral.
Can I ask a question?
Sure.
Sorry. A question about the finiteness of the integral. Does this conform with the usual expectation you would get by looking at the k representation of the integral? So, for example, for the bubble integral, which this corresponds to, you would say, well, in the loop integral, you have 4 powers of L in the numerator, 4 in the denominator, you get a logarithmic divergence. So in this, so what would the news be in this case if not 1, since that seems like it would say that it's finite?
So the news would be 1.
Or yeah, I guess that's a question. Like, what would the news be in the case of like a regular like 2 to 2 scattering in lambda 5 to the 4th bubble integral?
Yeah, that would be 1, right?
So then you would have a convergent integral.
No, that's divergent,
Oh, so sorry. If nu is greater than 0, then
right?
it's
So this
divergent.
in
Yeah.
4 dimensions, this bubble
Yeah.
integral is divergent.
Yeah. So,
And if you go
just to
to-
understand, when you say nu1 greater than 0, nu2 greater than 0, that's the condition under which that integral is divergent.
It's convergent,
It's convergent.
right?
Okay, so I'm confused then. So if for that bubble integral, nu1 and nu2 are greater than 0, why is it then that we know that that bubble integral is divergent?
Uh, right. Sorry. Okay, no. So this is actually convergent. That comes with the divergence here comes from the prefactor.
Okay.
From the
Oh,
gamma
I see.
function.
I see.
Right.
I see.
Yeah.
Okay.
So this is something that is excluded here.
Yeah.
Right. So this integral is actually then convergent in this
Yeah.
case. And the divergence, so there's like a prefactor that is a gamma of 0
yeah.
that we lost like in all these kind of
Yeah.
parametrization changes that I did.
Yeah. That
But
makes
yeah,
sense.
so one has to be careful about the divergences that come from the prefactors. And in many representations of these Feynman integrals, there you can factor off like the overall divergence, which is very convenient because this is like exactly the critical case, say in 4 dimensions, that this one is critically divergent. Yeah, so it's a finite integral in this parametric representation, but yeah, divergent in the momentum representation, for instance. And actually, it's also divergent in this representation, which is a bit different. So where you actually have 3 integration parameters. So yeah, it depends like which kind of representation you choose, but this Newton polytope picture tells you how you can check if it's finite or not, usually. So here's a different example. Yep.
From the example that we considered yesterday, we know that that's a beta function, right? And
Yep.
isn't that convergent for any negative real values of nu1 and nu2, except of course the simple poles had the negative integers.
The integral is not convergent so the integral is only convergent for nu positive, but there's an analytic continuation of the beta function. This is something that I'm going to talk about next. So you can analytically continue the beta function to all values of nu, but yeah, you have to do that by hand. So another example is this function here.
Yeah.
You probably know that you can also define it for negative nu's, but this integral here this integral representation is divergent if nu is 0 or smaller. So you have to do some analytic continuation tricks. And yeah, this is the same. This is actually a key property of these generalized Euler integrals as well, that these are kind of this is actually a special feature of these kind of functions, that you can perform this analytic continuation in the first place. It's kind of a magic property that it works, that you don't run into branch cuts, for instance. So if you look into these new dependence, then you can always analytically continue your integrals arbitrarily far. And the same for this gamma function. But it's a very cool property that you can, in fact, do this and don't run into trouble in multi-valued functions, with multi-valued functions. So let's just very quickly still talk about this slightly more complicated example. So this also comes from a Feynman integral, or you can get it from this banana integral that many people are also interested in. And here the Newton polytope of this thing looks a bit more complicated. So you have a triangle that lies in 3-dimensional space. And convergence happens always if this new vector lies inside this this triangle in three-dimensional space. So the region of convergence is always given by this interior of this Newton polytope. And as long as this S, so what's important is that because S is actually fixed by the sum of these new values, right? The important take-home message here is that if we are free to choose the news in any way we want, we always have some region of convergence. So we can always choose the news in such a way that we are lying in this Newton polytope, at least if there's not some degeneration of the Newton polytope. So if this is missing like some faces, or if the Newton polytope is squished to a too low dimension, then this doesn't work. But in the generic case, we can always find a set of news where we have convergence. And yeah, so this brings me to the next main statement on these integrals. So these integrals I, nu, n, they can be analytically continued to all complex values of these news meromorphically. So Cn minus some codimensional 1 set. So we can continue this to all points, like in n-dimensional complex space for these news, but we have to take out a codimension 1 set. So there's like some poles that we are setting out. So so meromorphically means that this I nu 1 function only has poles. At the singular codimensional 1 set. So it at most has pole singularities, so there's no branch cut singularities and no square roots or something like this. So everything is single valued, and there's a unique analytic continuation for all complex news. Yes?
Are they single poles, or are they?
They can be arbitrary high order.
Michi, going back to the first main theorem, is there any way to relax this condition to have the degree of divergence be bound in some way?
The degree of divergence is bound.
I mean, like only logarithmic like divergences, or up to linear divergences only.
You get logarithmic divergences if you are exactly on the boundary of the Newton polytope.
So I could take not just the interior but the boundary as well, and then you get only logarithmic. Can you keep like expanding this region and
Yes, so this is like the combination with this other property, maybe this meromorphic extension. So what you want to do is you want to perform this analytic continuation then to all values of C, and then you want to expand around certain points in the complex plane in these new parameters. So for instance, also around singularities. And you can do that. And this is also how you prove the meromorphicity. And I'm going to, in the last couple of minutes, briefly sketch via an example how to do that, how this works.
Thank you.
There's a trick that allows you to do that.
I'm sorry, can I ask a question?
So yeah,
So what happens to the faces of the Newton pole? I'm over here.
where are you? Yeah,
Okay.
I
What happens to the faces of the Newton polytope when we analytically continue to the complex to Cn?
what happens to the faces?
Because the integrals divergent on those
Yeah.
faces. So is that located inside of this codimension one?
Yeah, so actually the Newton polytope also tells you where the integral is divergent, so where the poles are. So it also so in a way you can actually what you can do is, if you know, like if you have convergence in some region, if this is your Newton polytope, then you know that there's like a divergence happening on these hyperplanes that bound the Newton polytope. And these are actually going to be iterated. So there's going to be a whole grid of poles. So this codimension one space set consists of all hyperplanes that bound the Newton polytope. So it's the boundary of the Newton polytope plus the extension to infinity. So plus like copies of these planes that are shifted by integers in all kinds of degrees. So you can learn something about this. But this works by the same trick that I still very briefly want to show you before the break. And I'm just going to explain it like in the very simplest example. And that also proves this meromorphicity, this trick. So again, the example is again this beta integral. And there's a diffeomorphism of projective space where we just rescale this object with some lambda. Or I mean, I'm actually running out of time, I think. Am I? I mean, do I have like 5 minutes? Okay, perfect. So we do the diffeomorphisms where we take pairs of homogeneous coordinates and map and just rescale one of the coordinates by some lambda. And lambda is some value larger than 0. And the magic of projective space tells us that this canonical form does not really care about this rescaling. So we can just do that. We get a different representation of the same integral, but we now have some free parameter in there. So the lambda pops out. And we have some lambda dependence in this polynomial. So now the trick is to do some kind of variation of integration by parts. But this is actually much simpler than normal integration by parts. It's just taking the derivative with respect to this 3-parameter lambda that we just introduced on both sides, and then immediately set this lambda to 1. So trick, take the derivative with respect to lambda, and then set lambda to 1. So if you take the derivative on both sides of this equation, on the left-hand side, we just get a 0. So this is pretty trivial. So we find 0. If we hit the right-hand side with a derivative of lambda, then something non-trivial happens. So we can hit it with this. We hit this first lambda term, the overall kind of divergence in this lambda rescaling that we choose. And we can also hit the polynomial, the lambda that appears in the polynomial. So we get 2 terms. And you can see that if we hit the first one, and then set lambda to 0, we only pick up a factor of lambda of mu1, and nothing else changes. So the first term just gives us mu1 times I nu I2, the original integral. So we did not very much. For the second term, we are actually in a bit of a more, I mean, it's slightly more complicated, but of course you also all know what happens. We are getting an extra factor of x1 out of this denominator, and we have to raise the denominator by 1. And then we pick up a minus, so small, a minus nu1 plus nu2 as the power that comes from taking the derivative of this denominator. And we can translate this again into an expression in terms of our original integral. So what we get is, if we permute this around, I times nu1 equals nu1 plus nu2 times I nu1 plus 1 nu2. And this looks very trivial, first of all, but we gained something now from nothing here. So this side of the expression is convergent. So we have a convergent integral representation for all positive values of nu1 and nu2 here. But here we have a convergent integral representation for all values of nu2 that are positive and all values of nu1 that are larger than -1. So here we are convergent. So here we have convergence for nu1 larger than -1 and nu2 larger than 0. So we increased, so because we can just take this now as a definition of this side, we successfully performed the analytic continuation. And if we shuffle this over, we see that the only thing that we did was we gained a pole in this new 1 parameter. And you can do these kind of tricks in a very high generality. So you can rescale like arbitrary parameters and then do this trick. You get an integration by parts relation, and each time, or yeah, if you don't do it like very clumsily, you extend the domain of convergence of your original integral, and you are then able to expand in more values of these news. And for physics, this is very useful because these news encode the space-time dimension, and we would like to expand an epsilon, for instance, in some kind of shift of the space-time dimension. And we are allowed to do this kind of expansion via these kind of tricks. And this also proves that there's a unique analytic continuation to the complete complex plane because we can do this for all parameters. And we can do this arbitrarily often, so it of course takes some time, but we can just repeat this process and we can get to some expression that is convergence for all nu, except for a specific number of poles that we have here. Okay, sorry for taking so much over time.
So in the interest of time, let's stop here for now, and we'll reconvene at 10:45.